After cutting it into 6 subintervals, we now need to choose our representative for each piece. The instructions told us how to do that. This is a midpoint Riemann sum. We need to find the midpoint of each interval. What's the midpoint between 1 and 5/3? Writing it as 3/3 makes it easy to see. The midpoint between 3/3 and 5/3 is 4/3. The midpoint between 5/3 and 7/3 is 6/3. Well, that's 2. Halfway between 7/3 and 9/3 is 8/3. That's 2 2/3. Halfway between 9/3 and 11/3 is 10/3. Halfway between 11/3 and 13/3 is 12/3. Well, that's 4. And halfway between here is 14/3. We got our representative values. Now what do you need to do? Now we need to choose those representatives and plug them into the function. What function? The function we're integrating, the integrand. We need f of 4/3. I'm not going to actually compute these yet. I want 1 over 4/3 squared. I want 1 over 2 squared. I want 1 over 8/3 squared. I want 1 over 10/3 squared. I want 1 over 4 squared. I want 1 over 14/3 squared. Then what do? I multiply each y value, each output value we computed, and we multiplied them by the length of the interval that it represents. Well, all these intervals are the same length. They all have a length of 2/3. So I need to take all of these and multiply them by 2/3. And then after that, we're going to add them up. All right, here's a tip. They're all getting multiplied by 2/3. They're all getting multiplied by the same thing and then adding them up. It's a lot less typing if we factor out that factor of 2/3. That's 2/3 times, like, way less typing if I take 2/3 times just those numbers. 1 over 4/3 squared, that's 3/4 squared will be less typing. Plus 1 over 2 squared, that's a fourth I can do right now. 1 over 8/3 squared, 1 over 8/3 is 3/8, so this is 3/8 squared. 1 over 10/3 squared is 3/10 squared. 1 over 4 squared is 1 over 16. 3 over 14 squared. So I want 2/3 times this sum. Let's type that in. I won't make you watch me type this. There, I typed it. 2/3 times each of those things squared. Oh, I accidentally put a minus instead of a plus. Let me fix that. Plus. So that's plus that, plus that, plus that. Yeah, I think we typed this right. I need parentheses to make sure the whole thing is squared. I'm getting 0.76769. So we're getting that the integral from 1 to 5 of 1 over x squared dx is about 0.76769. How accurate is that? If this was a derivative, I might say now do it over and over until you know how many digits you're right. You don't want to do that here. We're going to use the word Riemann sum. I'm going to give you way more specifics when I tell you to estimate it, because just saying do it over and over is not reasonable. It's worth noting, though, this is a thing our calculator can compute. How do you get your calculator to give you digits? Let's look at that. I guess also, your calculator can do an integral. Step 1 is you need to graph the integrand. Here, that's 1 over x squared. I go to y equals, I graph the function, not that function, I want the function, 1 over x squared. Graph it. This is the default window from -10 to 10. You don't need to do the default window, but the important thing is that your window needs to include the interval that you care about. I'm going from 1 to 5. So my graph needs to at least go from 1 to 5. Here it is going from 0 to 6. Let's zoom in on the y-axis a little bit. Let's just go there from 0 to 2. Includes everything we care about, I think. There we go. Now, So graph the integrand. Your graph needs to include the interval on the x-axis. Now we need to go into the calc menu. We get there by hitting second and then trace, or at least on my calculator. If you have a different TI, it might have it organized differently. Mine is on second. Trace is the calc menu. Hey, by the way, you can compute derivatives in here. That's not nearly as valuable as it is for integrals, but the seventh thing down is the integral of a function. So on mine, it's 7 is the integral f of x dx. When we do that, it's going to ask us what are the limits of integration. This is another word for the bounds of integration. We haven't told it that we want to integrate it from 1 to 5. This is the lower limit is 1. This is the upper limit is 5. I'm more likely to call them the lower bound and upper bound. The calculator uses limit. So our lower limit is 1. You can arrow over, but that's dumb. Just type in the number 1. What's the upper limit? The upper limit is 5. As it computes it, it shades in this thing. We got the answer is 0.8 exactly. So this is the lower limit. This is the upper limit. Oh, I made a big deal on the first day of class that we're not talking about limits. That's a different use of the word limit. The answer. So our estimate was 0.76769. The actual answer appears to be 0.8. We'll have reason to care about these, but it's worth noting, like you might want to feel like, hey, I'm going to skip the Riemann sum by just getting the answer. When I'm giving you these problems, I'm often going to tell you, hey, you must compute the Riemann sum. Often I'll also say I'll compute the integral because it's pretty easy to get your calculator to give you the exact number. And then you can check how good was your estimate. Here, this estimate was pretty good. Midpoint estimates are usually much, much better than upper and lower estimates, or left endpoint or right endpoint estimates. We haven't talked about upper and lower enough. Let's do that as our next example.